Another type of growth model is a logistic growth model. A logistic growth model is appropriate for a situation where we would normally be growing exponentially. However, there is some external limit on how large our quantity can grow. These are very common in population growth models because the environment will not sustain an unbounded growth in population. This is the formula that we are using for logistic growth. And this is where we only have a recursive model here. We don't have an explicit model. So to find the size of a population after n time periods, we have to use the previous time period as p sub n minus 1. And we've got the r, the growth rate, and then k is what's called the carrying capacity of the environment. Now, the exponential growth model, let's just draw a quick picture so we are clear. With exponential growth, we have a population that starts off somewhere, and it starts to grow, but as we go, it just kind of shoots up, okay, pretty fast. This would be exponential. Exponential. However, for a logistic growth model, we have a carrying capacity, call it K. And for these, we start out with a population and we start to grow, but as we get closer to that carrying capacity, we have to slow down, okay? And sometimes we'll be a little bit underneath it and then we'll grow a bit, but if we go over that carrying capacity, our environment will force us back down, and so we'll come down, and then we just kind of start to bounce around, okay, that carrying capacity. Okay, so that's kind of what the logistic growth model looks like. Let's go ahead and look at an example. A forest is currently home to a population of 200 rabbits. The forest is estimated to be able to sustain a population of 2,000 rabbits. Absent any restrictions, the rabbits would grow by 50% per year. Predict the future population using the logistic growth model. So, our logistic growth model is P sub n equals P sub n minus 1 plus R times 1 minus P sub n minus 1 over K times P sub n minus 1. Our current population is 200. That's going to be the P sub n minus 1. So we have a 200 plus R is the growth rate that we would have with unrestricted growth. That's the 50%. So 0.5 times 1 minus the 200 over the carrying capacity K, which in this case is the 2,000 that the forest would be able to sustain. So 2,000 times the P sub n minus 1, which is the 200. Okay, this is going to be our, after one time period, what we would end up with. Go ahead and plug this into our calculator to get that estimate. 200 plus 0.5 times 1 minus the 200 over 2,000 times the 200. Okay, this gives us a population of 290. So after one time period, we would have a population of 290. To get our next time period, okay, after another breeding cycle, we then use that as our P sub n minus 1. So now we'd have 290 plus R, which is 0.5, times 1 minus 290 over 2,000 times the 290. So now let's go ahead and plug that into our calculator. 290 plus 0.5 times 1 minus 290 over 2,000 over 200, or sorry, times 290. And that gives us, and if we round this to the nearest whole number, because we're talking about a rabbit population, that'd be about 414. 414. So that's going to be our population after 2 breeding cycles. So this is how the logistic growth model works.